You know, when you see a crackling fire, or a rusty old nail, or even just take a breath, what do those things all have in common? Well, they're all written in the fundamental language of the universe, chemical reactions. And today, we're going to learn how to read that script. It's a weird question, right? One is this super fast, fizzy thing you do for a science fair, and the other is this incredibly slow, quiet process of decay. But the answer is, at their core, they are both chemical reactions. They're both about stuff fundamentally transforming into, well, new stuff. All right, so what's our game plan? In this explainer, we're going to start by playing detective, learning to spot the signs of a reaction. Then we'll become chefs and figure out how to write the chemical recipe. After that, we'll dive deep into reactions that happen in water. And finally, we'll build ourselves a field guide to classify everything we find.
Okay, first things first. How do you even know when you're looking at a chemical reaction? I mean, are there clues? It turns out the universe gives us some pretty obvious ones if you know what to look for.
Think of these 5 things as chemical fingerprints. If you see a dramatic color change, or bubbles suddenly appearing out of nowhere, or a solid forming in a totally clear liquid, or it suddenly gets hot or cold, or starts glowing, you're not just seeing something cool. You are literally witnessing atoms being rearranged.
Let's go right back to that baking soda volcano. We all know what happens, right? You mix the vinegar and baking soda and fizz, bubbles everywhere. Those bubbles? That's carbon dioxide gas, a brand new substance that wasn't there a second ago. That's our proof right there that a reaction just went down. So seeing the signs is one thing, but to really understand it and to tell other scientists what happened, we needed a universal language. And that language is the chemical equation. A chemical equation is honestly just a recipe. On the left side, you've got your ingredients. We call them reactants. And on the right side, you have what you made, the products. That arrow in the middle, it just means turns into or produces. Simple, right? But there is one cosmic rule you can never, ever break. And this is it, the law of conservation of mass. The best way to think about it is like cosmic bookkeeping. Every single atom you start with has to be accounted for at the end. They can swap partners, they can form new molecules, but they can't just poof into thin air or appear out of nowhere. Let's look at the recipe for water. That unbalanced equation on the left, that's a huge problem. It says we start with 2 oxygen atoms, but we only end up with 1. That's chemically illegal. To fix it, we use coefficients, those big numbers out front. The balanced equation on the right shows that it takes 2 hydrogen molecules and 1 oxygen molecule to make 2 water molecules. Now everything adds up. The universe is happy. Now, balancing might look a little intimidating at first, but it's really just a puzzle. It's a logical process. You list your elements, you count them up on both sides of the arrow, and then you just start plugging in coefficients to make the numbers match. Once you get the hang of it, it's actually pretty satisfying. Okay, so we know how to write the recipe, but a ton of these reactions happen in water. And to really, truly understand what's going on inside a solution, we have to peel back the layers, kind of like an onion. So the first layer, the outside of the onion, is the molecular equation. This is the big picture overview. It shows all the complete whole compounds involved. Here we've got sodium hydroxide and hydrochloric acid reacting to make plain old table salt and water. It's correct, but it's not telling us the whole story. Let's peel that layer back. This is the complete ionic equation. See, because these things are dissolved in water, they don't stay as whole molecules. They actually break apart into their ions. So suddenly, we can see all the individual players floating around in there, the sodium ions, the hydroxide ions, all of them. And now for the final layer, the very core of the onion. Did you notice how the sodium and chloride ions are on both sides of the equation? They haven't actually done anything. They're what we call spectator ions. They're just hanging out, watching the show. So, if we remove them, we get to see what's really going on, the main event. The core reaction here is just a hydroxide ion and a hydrogen ion coming together to form water. That's the chemistry. So there are millions, probably billions of possible chemical reactions. Sounds totally overwhelming, right? Well, the good news is most of them fall into just a handful of major categories. So think of this as your field guide for identifying reactions out in the wild. This table really helps organize the chaos. So let's run through them. You've got synthesis, 2 things combined to make 1 new thing. Super simple. Then there's its opposite, decomposition, which is a chemical breakup. One compound splits apart. Single replacement is when one element cuts in and swaps places with another in a compound. And in a double replacement, it's like two couples just swap partners. And finally, the flashy one, combustion. That's just when something reacts with oxygen and usually gives off heat and light, fire. Learning these patterns is a game changer.
So, why does all this matter? Well, think about it. We've gone from just noticing some bubbles to writing the precise recipe to seeing the true action in a solution, and now to actually classifying the event. This isn't just about memorizing rules. It's about learning a powerful system that lets you predict and even control the chemical changes that shape our entire world.
We've gone from just spotting bubbles to actually reading the recipes of the universe. You now have the basic tools to decode the chemical language that's written all around you, every single day. So the only question left is, what reaction will you decode next?